Good morning dear students. In the last video we learned basic properties of electric charges, Coulomb's law, limitations of Coulomb's law, absolute permittivity of a medium, relative permittivity or dielectric constant, force between multiple charges. So many things we learnt in the last class. Today let us understand few more concepts on the first chapter, that is electric charges and fields. In that, the first concept is electric field. The statement for the electric field as follows: the region of space around a charge or group of charge within which other charged particle experience electrostatic force is called electric field. So let us understand the electric field by using simple diagram. So I consider positive point charge. So this is the region of a space around a charge. So within this region I am bringing other charged particle, say plus Q naught. So if you brought other charged particle within this region, it experiences electrostatic force. If other charged particle experience electrostatic force within this region, then the region of a space around a charge is called electric field. So this region of space around the charge is called electric field. And what I consider a positive point charge, it is producing an electric field around it. This point charge is called source charge. And what we brought to check the electric field around the charge, that charge is called test charge. Test charge. Test charge is nothing but it's a small charged particle experience electrostatic force in an electric field. Test charge is also called as detector of electric field. Source charge means the point charge producing electric field around it. This source charge may be a point charge or group of charge. So here we can notice there are three concepts are there. First one is electric field, then source charge, then test charge. Electric field, the region of space around a charge or group of charge within which other charged particle experience electrostatic force is called electric field. So this is a region of space around a charge. Source charge is nothing but point charge producing electric field around it is called source charge. Source charge may be a group of charge. Test charge is nothing but it's a small charged particle experience electrostatic force in an electric field. Test charge is a detector of electric field. So this is all about electric field. Then the next concept is electric field intensity or electric field strength. It is denoted by E. Look at the statement. Electric field intensity at any point in an electric field can be defined as force experienced per unit positive charge placed at that point, which means we need to calculate the strength of electric field or intensity of the electric field at any point in an electric field. Let us consider the same diagram. So this is a point charge or a source charge producing electric field around it. Just now I explained. Now at any point in an electric field, say this point, say P. So in this point we need to calculate the strength of electric field. So according to this statement, to calculate the strength of an electric field at any point in an electric field, we need to keep unit positive charge or test charge. So I am keeping Q naught, test charge or unit positive charge. If you keep test charge at a point P in an electric field, definitely it experiences electrostatic force. That force experienced per unit positive charge gives the strength of electric field. So it can be calculated at any point. Here also we can calculate, here also we can calculate, here also we can calculate. So we can calculate the strength of an electric field at any point in an electric field. So the strength of electric field is nothing but force experienced per unit positive charge placed at that particular point. So mathematically we can represent E is equal to F by Q naught. So this is the equation for electric field intensity. Electric field intensity, force per unit positive charge placed at that point. Electric field intensity is a vector quantity. SI unit of electric field intensity. SI unit is, look at this, SI unit of force is Newton, SI unit of force is Newton, and the SI unit of charge is Coulomb. So Newton per Coulomb. And the direction of electric field intensity is same as the direction of motion of unit positive charge. So this is all about electric field and electric field intensity or electric field strength. Now let us understand what exactly the uniform electric field and non-uniform electric field. First one, uniform electric field. It is an electric field in which unit positive charge experience same force at all the point. Then the electric field is said to be uniform electric field. Suppose, for example, look at this diagram. We have marked many points, 1, 2, 3, 4, 5. So we can keep a unit positive charge at any point in an electric field. Suppose if you are keeping in this point unit positive charge is experience a force, for example 4 Newton. Now we are keeping the same unit positive charge in a different position. There also it experience same force. If it is experience same forces at all the point, then the electric field is said to be uniform electric field. Next one, non-uniform electric field. It is opposite to that. It is the electric field in which unit positive charge experience different forces at different points. For example, in this point, suppose the unit positive charge experience 4 Newton. In this point, it may not 4 Newton. It may experience 6 Newton. The one more point, it may experience 8 Newton. So the force experience per unit positive charge is different at different points. Then the electric field is said to be non-uniform electric field. Next note, the first one, if the source charge is positive, the direction of electric field is directed outwards. Look at the nature of the diagram. See, this is source charge, the positive source charge. If the source charge is positive, the direction of electric field is directed outwards like this. Similarly, if the source charge is negative, the direction of electric field is directed inwards. Right here, second diagram. See, negative source charge. So the direction of electric field directed inwards. Why the direction of electric field is directed outwards in case of positive charge, and why they are directed inwards in case of negative charge, you will get to know in a further explanation. The next concept is electric field intensity due to a point charge. So here we are finding electric field intensity by using a point charge. Now I am going to consider a point charge, positive point charge placed at a point O, and this point charge producing electric field. So at any point in an electric field we need to find electric field intensity. So I am going to mark a point P. The distance between the point O and the point P is taken as R. To find electric field intensity at a point P in an electric field, we need to keep unit positive charge in that particular point. Now I am keeping unit positive charge plus Q naught. Now the force experienced by unit positive charge due to the point charge according to the Coulomb's law, we can write F is equal to 1 over 4 pi epsilon naught. Here we have Q, in this point we have Q naught divided by what is the distance between a point charge Q and the unit positive charge Q naught. It is R. According to the Coulomb's law, it is R square of the distance between them. But we are calculating electric field intensity. We have already mathematical expression for electric field intensity, that is E is equal to F divided by Q naught. Then E is equal to, what is the F we got? The force between the point charge and the unit positive charge, 1 over 4 pi epsilon naught Q naught divided by R square divided by Q naught. So here we can cancel Q naught. And the remaining thing, E is equal to 1 over 4 pi epsilon naught Q divided by R square. So this is the expression for electric field intensity due to a point charge. This is electric field intensity due to a point charge. We can express in terms of vector form. E vector is equal to 1 over 4 pi epsilon naught Q divided by R square R cap. R cap is unit vector in the direction of electric field intensity. I'll brief you once again. So here we are talking about electric field intensity due to a point charge. So I consider a point charge at the point O. It is producing electric field. At any point in an electric field, we are marking the point as a P. In that point I am keeping a unit positive charge, that is plus Q naught. The distance between both the charges is R. Then definitely there is an electrostatic force between these two forces, that is given by, according to the Coulomb's law, F is equal to 1 over 4 pi epsilon naught Q naught divided by R squared. But we are calculating electric field intensity. So we have a mathematical expression for electric field intensity, that is E is equal to F divided by Q naught. We have a value for F. So E is equal to, in the place of F, we are substituting 1 divided by 4 pi epsilon naught Q naught divided by R square, and divided by Q naught is there. Q naught get cancelled. The remaining thing, E is equal to 1 over 4 pi epsilon naught Q divided by R square. So this is the magnitude of electric field intensity due to a point charge. So in terms of vector form, we can write it like this. E vector is equal to 1 over 4 pi epsilon naught Q divided by R square R cap, where R cap is the unit vector in the direction of electric field intensity. I have written only EF. It is nothing but electric field intensity. So this is all about electric field intensity due to a point charge, and very important for 3 marks. We can expect for 3 marks in a board examination. Next concept is electric lines of force or electric field lines. Look at the statement. Electric lines of force in an electric field is an imaginary straight or curved path along which a unit positive charge moves. So let us understand what exactly the electric lines of force. Now I am going to consider positive charge. Positive charge I consider. Now I am bringing unit positive charge. I am bringing unit positive charge near to this positive point charge. Here also I consider positive charge. Here also I am bringing unit positive charge. What is the nature of the force between them? Definitely there is a repulsive force, which means this unit positive charge moves away from the positive point charge, means they start moving like this. Along the motion of the direction of unit positive charge, I am writing an imaginary lines. That imaginary line is nothing but electric field lines. Let us check it out for negative charge. So negative point charge, now I am bringing unit positive charge near to the negative point charge. What is the nature of the force? Force of attraction, which means the unit positive charge moves towards the negative point charge. It will move like this. Along the direction of the motion of the unit positive charge, I am writing imaginary line. That imaginary lines is nothing but electric lines of force or electric field lines. I will brief you. Electric lines of force in an electric field is an imaginary straight or curved path along which a unit positive charge moves. Along the direction of motion of unit positive charge, we are writing one imaginary line. That imaginary line is known as electric lines of force or electric field lines. Question will arise, when does the electric lines of force become straight? When does the electric lines of force become curved? Let us understand. Electric lines of force are straight when they represent electric field due to an isolated charge. Look at the nature of the electric field. Now, isolated charge. Here the electric field is represented due to isolated charge. Then the electric lines of force are straight. Similarly, electric lines of force are curved when they represent electric field due to two or more charge placed nearby. Look at the nature of electric lines of force now. Positive charge, here negative charge. Electric lines of force are curved when they represent electric field due to two or more charge placed nearby. So electric lines of force are straight when they represent electric field due to an isolated charge. Electric lines of force are curved when they represent electric field due to two or more charge placed nearby. Next is properties of electric lines of force or electric field lines. Let us understand what exactly the properties of electric field lines or electric lines of force. The next concept is properties of electric field lines or properties of electric lines of force. Let us understand one by one. The first one, electric lines of force originate from positive charge and terminate on negative charge. First property, electric lines of force originate from positive charge and terminate on negative charge. Electric lines of force or normal to the surface of a charged conductor. which means they are always normal to the surface of a charge conductor. Third one, two electric lines of force never intersect one another. They never intersect one another. Fourth one, electric lines of force are crowded right here. Electric lines of force are crowded in the region of stronger electric field and they are further or they are spread out. They are spread out in the region of weaker electric field. Fifth one, electric lines of force do not pass through a conductor. Sixth one, electric lines of force reveals nature of electric field. So these are the properties of electric lines of force or electric field lines. Again, I am going to explain one by one. The first property, electric lines of force originate from positive charge and terminate on negative charge. In the previous diagram, I hope you noticed the direction of electric lines of force. They are originated from positive charge and terminated on negative charge. The second one, electric lines of force are normal to the surface of a charge conductor. The electric lines of force always normal, means perpendicular to the surface of a charge conductor. Third one, two electric lines of force never intersect one another. I hope you have observed in the last diagram, two electric lines of force never intersect one another. And the fourth one, electric lines of force are crowded in the region of stronger electric field and they are spread out in the region of weaker electric field. For example, if it is strong electric field, means they are crowded like this. They are crowded in the region of stronger electric field. In the region of weaker electric field, they are spread out. I'll write here like this. They are spread out. They are spread out. Look at the difference. They are crowded in the region of stronger electric field. They are spread out in the region of weaker electric field. And fifth one, electric lines of force do not pass through a conductor. Why? Because in basic properties of electric charges we learn, electric charges always resides on the outer surface of the electric field. So inside the conductor there is no electric charges. The same way, electric lines of force do not pass through a conductor. The sixth one, electric lines of force reveals nature of electric field. The nature of the electric field. What is the nature of electric field? If I consider negative point charge or negative source charge. What is the nature of electric field? If I consider positive source charge. What is the nature of the electric field? If I consider similar charges. What is the nature of the electric field? If I consider unlike charges, like charges or unlike charges. So everything it reveals, electric lines of force reveals nature of electric field. So these are the properties of electric field lines or electric lines of force, very important for 3 marks. Any 3 you can write in the examination. The next concept is electric dipole. Look at the statement, It's a pair of equal and opposite charges separated by a small distance 2a, that is negative charge and one positive charge. Pair of equal and opposite charges separated by a distance 2a. Negative charge and positive charge, pair of equal and opposite charges separated by a small distance 2a. Here the 2a is called dipole length. Dipole length. And the straight line which is joining a negative charge and a positive charge and directed from negative charge to the positive charge is called axis of dipole. Axis of dipole. So this is what axis of dipole. I repeat, the straight line joining negative charge and positive charge and directed from negative charge to the positive charge is called axis of dipole. First one dipole length, second one axis of dipole, the third one the straight line passing through the negative charge and positive charge is called axial line. Axial line of dipole. And one more thing is there, the fourth one, the line, this is the midpoint of a dipole, say O, the line perpendicular to the axial line, this is the axial line, the line perpendicular to the axial line passing through the midpoint of the dipole is called equatorial line. Right here. Equatorial line. So along with electric dipole we have a 4 different statement. Electric dipole, pair of equal and opposite charges separated by a small distance 2a. So this is the electric dipole. Along with that electric dipole we learn dipole length. Dipole length is nothing but the distance between two charges of an electric dipole. Axis of dipole is nothing but the straight line joining negative charge and positive charge and directed from negative charge to the positive charge is known as axis of dipole. Then the third one, axial line of a dipole. Axial line is nothing but the line passing through the negative charge and positive charge is known as axial line. The fourth one, equatorial line. The line perpendicular to the axial line and passing through the midpoint of an electric dipole is known as equatorial line. Next concept, electric dipole moment is indicated by P, electric dipole moment. Electric dipole moment of an electric dipole can be defined as product of magnitude of either charge and the distance between the charges of an electric dipole. I repeat, electric dipole moment of an electric dipole can be defined as product of magnitude of either charge and distance between the charges of an electric dipole. You can consider this diagram. So electric dipole moment is represented by P and it can be defined as product of magnitude of either charge. You can take any magnitude of one charge, for example Q. Product of distance between the two charges of an electric dipole. What is the distance between the two charges of an electric dipole? 2a. So this is the equation for electric dipole moment. I repeat, electric dipole moment of an electric dipole can be defined as product of magnitude of either charge and the distance between the two charges of an electric dipole, that is P is equal to Q into 2a. And one by one, what is the use of electric dipole moment? Electric dipole moment is a measure of electric dipole, means to calculate the strength of the electric dipole we are using electric dipole moment. The first one, electric dipole moment is a measure of strength of electric dipole. Second one, it's a vector quantity. It is a vector quantity. And third one, the direction of electric dipole moment is from negative charge to the positive charge always. The direction of electric dipole moment is from negative charge to the positive charge of an electric dipole. And SI unit is, look at the SI unit. What is the SI unit of charge? Coulomb into the distance. What is the SI unit of distance? Meter. So coulomb meter. One more SI unit is there, that is D by. 1 D by is equal to 3.33 into 10 to the power of minus 30 coulomb meter. And one more thing you can observe, net electric charge of an electric dipole is 0. Look at the last point. Net is nothing but total. Net electric charge of an electric dipole is 0. Means total electric charge of an electric dipole is 0. Why? Because look at this electric dipole. Net, this is equal in magnitude and opposite in direction. So they are cancelled. So the net electric charge or total electric charge of an electric dipole is 0, but electric field is not 0. So this is all about electric dipole moment. Under the concept of electric dipole, we learned dipole length, axis of dipole, axial line, equatorial line, and now electric dipole moment. This is the equation for electric dipole moment. P is equal to Q into 2A. Electric dipole moment is a measure of strength of electric dipole. It's a vector quantity, and the direction of electric dipole moment is from negative charge to the positive charge. SI unit of electric dipole moment is coulomb meter or D by. 1 D by is equal to 3.33 into 10 power minus 30 coulomb meter. It's not a centimeter, it's a coulomb meter. And last point, net electric charge of an electric dipole is 0. Why? Because pair of equal and opposite charges. Equal in magnitude, opposite in direction. So both will cancel. So total electric charge of an electric dipole is 0, but electric field is not 0. Today we learned electric field intensity due to a point charge, and electric lines of force, properties of electric lines of force, electric dipole moment. In the next class, we will discuss a derivation on the basis of electric dipole and electric field intensity. Thank you.